Welcome to lesson 2 in our series on gravitational phenomena and orbital motion. And this one will focus on gravitational force. So yesterday we asked our listeners and viewers to imagine a universe occupied by a single object. And well, in that lonely universe, the only thing that an object can do by its nature as a mass is to create gravitational field. All right, that is half of the nature of mass, is that masses create and can be affected by gravitational field. In a universe occupied by a single object, the only thing that object can do is create a gravitational field. All right, now what we say is, what if this universe was occupied by two objects? Well, what happens is each of these objects is now located in the field made by the other one. So object 2 is located in the gravitational field made by object 1, and vice versa. Object 1 is located in the field made by object 2. And so what happens? What happens when an object is located in a gravitational field made by another object? Well, the result of that is that a gravitational force is experienced by each object. Each of these objects exerts a gravitational force on the other one. Now, these two terms, gravitational field, gravitational force, can be tricky to keep straight. But as a physics student, that's part of your job. Okay, so we have to be okay with the fact that this gravitational field is what we call a lowercase g. Gravitational force we will call F with a subscript g. All right, and so what we've said, most folks are okay with, well, how strong is a gravitational field that an object experiences? Sorry, well, see, look at me. I already screwed it up. How strong is the gravitational force that an object experiences? Well, that depends. It depends on how much mass the object has and the strength of the field that it's in. Okay, so these two objects, well, if we want to know how much gravitational force is exerted on object 2, what I would say was there's a force that looks like this. Here's Fg on 2 by 1, and that's equal to M2 and G1. So how much force is exerted on 2? It depends on 2's mass and the strength of 1's field. Well, here's a force exerted on object 1, and that Fg on 1 by 2 is equal to, well, let's see, 1's mass and the strength of 2's field. And when I say the strength of 1's field or the strength of 2's field, what we mean by that is, remember that this gravitational field, G, let's do this, G is Gm over r squared. So, like at the location of 2, really everywhere on that sort of circle, not really a circle, is it? I'm trying to draw part of a circle that's the same distance r away, that's probably better, from object 1. Sure, everywhere on that circle, well, G1 is big G M1 over the distance from 1 to 2 squared. And G2, right, is G M2 at the distance from, I guess we could say 2 to 1 squared. Well, R12 and R21 are the same thing. So look at what happens here. The magnitude of these gravitational forces, if we write, well, Fg on 2 by 1 is M2 times G1. That's big G, M1 over R1 to 2 squared. And look at this. What's the magnitude of the force that is exerted on 1 by 2? Well, that depends on mass 1 and G2. And guess what? Those are the same exact thing. I mean, algebraically, arithmetically, it's the product of big G and the two masses, divided by the square of the distance between them. So we can say that a gravitational force on one object by another is gm1 m2 over r squared. And maybe we throw a r1 to 2 in there. All right? And we have to notice that for a couple of reasons, those forces are what we call equal and opposite. One is because they are a force pair, and Newton's third law defines the fact that when objects exert forces on each other, those forces must be equal in size and opposite in direction. And so we showed quite literally here that, when we take this assumption for how strong a gravitational field is, those answers come out to be algebraically equivalent. So in green is the general expression for the gravitational force that one object exerts on each other. What you need to know is the mass of each object and the distance between them. All right. Notice I haven't said the word radius. Now you'll start saying it. But this r means, remember, r locates one thing relative to another. It's a distance from one place to another. Okay, so fight the urge to say radius. And this r does not mean radius. Okay, so let's use this expression and talk about some of the quantitative nature of it. And we're going to say, let's assume that these two masses assume a force that we'll call F naught on each other. Well, that means we can define force F naught apparently as, well, G M M over D squared. D happens to be the distance from one object to another, which is what r means. And when we say one object to another, here's real important, real important. This distance here, r, let's see, I'll put this right over here. Let's just put it over here. R is distance between objects' centers. Just like r yesterday was the distance from the center of one object to a location in space. Well, that's why this distance is from the center of one object to the center of another. There's this r. Okay. Now, in this case, the magnitude of that r happens to be called capital D. So there's a definition of F naught. We could go a step further if we wanted and say, since these are identical masses, m times m is m squared. There's a definition for this F naught. So in terms of F naught, let's talk about, or let's write expressions for, what are the forces that these other objects exert on each other. Here's case 2. Well, in case 2, we can say F2 is big G, m times 3m over 2d, but that distance is squared. So that's going to be, let's see, 3 gm squared over 4 d squared. And notice here is that. That's F naught. So F2 is 3/4 F naught. All right, these just get us some practice with working with the algebraic relationships that are inherent to this expression for gravitational force. Okay, just be careful. M times 3m is not 4m. M plus 3m is 4m, but there's no pluses in here. There's no adding of masses. All right, here's another one. Let's call this case 3. We have F3 is G times m times m over 2 over d over 2 quantity squared. So let's see, that's G m squared over 2 divided by d squared divided by 4. Let's see, that's G m squared over 2 times 4 over d squared, right? Divided by a fraction is the same as multiplying by its reciprocal. All right, so that's G m squared over d squared. I'm trying to get that F naught again, times 4 over 2, right? there's F naught. So this is 2 F naught. F3 is twice as strong as the baseline F naught. Finally here, let's say in 4, F4 is, let's see, G times, watch this, 6m squared. 3m times 2m is 6mm. All right, it's not, so that's an important thing, I guess, to show. For a lot of my students have a tough time with doing this. They'll say, okay, well, that's like 5-2m or something. Absolutely no. Right? 3 times 2 is 6. M times m is m squared. Okay? Get all the numbers together, get all the m's together. Okay, divided by 3d, quantity squared. That's 6g m squared over 9d squared. Right? That's 2/3 F naught. Okay, so of what interest is this? I don't know, but what it does let us do is say, hey, you know, this is the fundamental relationship that defines how much force objects exert on each other. So if something changes by certain factors, how does that affect the overall force? And as physics people, we ask those types of questions. Okay, now a little more practical, perhaps. Let's imagine a free fall scenario. In typical free fall scenarios, you know, what we do is we say, hey, in this room or near, quote, near the surface of Earth, if something free falls, well, that means that it accelerates downward at 9.8 meters per second per second. And that acceleration is constant. But when we look at things at this scale, the reason that a lot of free fall cases have constant accelerations or yield constant accelerations is because gravitational field near the surface of Earth is constant. All right, but at this scale, gravitational field is not constant. Right? We said yesterday that if there's a gravitational field here of g, well, twice as far away, gravitational field is now 1/4 as much. 3 times as far away, gravitational field is now 1/9 as much. 4 times as far away, gravitational field is now, did I say 9 times? Or 1/16 as much. So gravitational field is vastly different when you start looking at, or differs vastly when you start looking at scales that are not, quote, near the surface of a planet. All right, so if we want to say that these objects are located a distance r apart, and again, that is a center-to-center distance, big M's gravitational field at M's position, well, remember, here's an expression for gravitational field. The field made by M is g times M's mass divided by the distance from M center to our point of interest. And that point of interest happens to be where little m is located. All right, so that means we can say, well, here's a gravitational force on little m by big M. We can use that to write a net force statement. Because if we want linear acceleration, well, that sort of screams at us to say, okay, let's do net F equals ma. And quite literally, if I'm saying little m, that's little m. Little m's acceleration, well, the net F is fg on little m by big M equals little m a. Well, fg is big G, little m big M over our r squared. And this is little m a. And notice, a lot like we've seen before, the mass of the object that's accelerating due to gravity is irrelevant. And so here's A's acceleration. It's G big M over r squared. Look at that. Those are the same thing. So we saw yesterday the simplest free fall case, you know, if we say here near Earth, we just say, well, there's mg, right? And mg equals ma. And that's when we said, well, this is gravitational mass. This is inertial mass, but they are experimentally verified to be equivalent. And so A and g are the same thing. I mean, they don't mean the same thing. G quite literally means gravitational field. A means acceleration. But Earth's gravitational field of 9.8 newtons per kilogram at the surface yields a free fall acceleration of 9.8 meters per second squared at Earth's surface or near Earth's surface. But in general, an object's acceleration is going to be equivalent to the strength of the field that it's in, no matter where that is. This just happens to be at Earth's surface. This is our expression for gravitational field strength anywhere. And remember, if we used big R, meaning Earth's actual radius, or planet's actual spatial radius, big R, that GM over big R squared would get us gravitational field strength at surface. All right, so the deal is, if we want to know how fast something accelerates anywhere, because of the field that it's in, well, we need to know the strength of the field. And then that's the answer. And this just shows us, right, since acceleration is proportional to the inverse of r squared, that means that this graph, if we look at acceleration as a function of r, I mean, the way you do this, here's a way to do this. You say, let's start with a point like here and here. Will this work? Probably. Now, so there's a data point. At some r, you get some a. This says if you double r, well, what happens to a? If you double r, then a gets not half as big, but 1/4 as big. So we take this and we go down by 4. So here's another data point. And then if this r were to get cut in half, this gets 2 times smaller. A gets 2 squared times bigger. So this gets 4 times bigger. There was A, there's 2A, there's 3A, there's 4A. So here's another point up here. And what we get is this pretty sharp, that doesn't go back up, careful about that. Pretty sharp. Yeah, sort of. Watch this. I have the luxury of sliding this thing around a little to make it yeah, that's nice. Right? We will never get an A of 0, or an object will absolutely always, will always accelerate when it's in some other object's gravitational field. But that acceleration just might get really small, right? Acceleration gets really small as r gets really big. Or when r gets really small, a gets really big. Right? So that's qualitatively the nature of an inverse relationship. The inverse square is a little bit different because we have to say that whatever happens to r, the opposite squared happens to a. The squared is really important. Lastly here, a question might say, hey, what does m weigh? What does little m weigh at distance r? Well, what that's really asking for, weight, is that, right? So the weight is the gravitational force on little m by big M. And so there we simply use the expression for the gravitational force that one exerts on the other. And guess what? You're going to be asked that question where it says, well, the moon is 1/81st the mass of the Earth. The Earth is 81 times the mass of the moon. Compare the size of the gravitational force they exert on each other, and you'll say, well, it's got to be 81 times this, or wait, is it 9 times because there's a square in the, nope. The answer is the two forces are equal and opposite no matter what, right? If I've drawn this force that is exerted on little m by big M, then here is the same exact force on big M by little m, force pair. What happens is, it might be that big M makes a strong field out here, and little m is a weak mass, or a small mass. So a small mass and a strong field. Okay, well, this is a big mass in a weak field, and those two things balance out. Okay, so bottom line here, folks, is this is the way to express the gravitational force that two objects exert on each other. That is different than gravitational field. All right, field is not force. Force is not field. You gotta do what you can to keep those two things separate in your mind. Okay. Another nice thing about gravitational force is, as when we use this sort of on-by notation, that really tells us, it really defines for us the fact that for there to be a force, there have to be two objects that are interacting. That is what interaction is. That's what forces are. Forces are interactions between objects. Interactions are objects exerting forces on each other. So there have to be two different objects when you are expressing a force. But a single object on its own makes a field. So when we say field, we only need one object. You don't need two objects for there to be a gravitational field. Okay? So, do what you must to keep those straight, but you must. All right? Be sure you're okay with this great application of Newton's third law, that because we know it to be a fact. Well, we have just said it many times to be a fact, but this gives us some nice algebraic proof that these two forces that objects exert on each other are algebraically equal and opposite. Well, at least algebraically equal, right? And gravitational forces, what they do is attract every object to every other object. Listen to that, every object to every other object. Right now, you are exerting a gravitational force on every object in the universe. Let that sink in a little bit. Every single object in the universe is pulling on you. Most of those forces are super duper small, especially as compared to the force that Earth exerts, but they're there. Okay, this gives us some practice with algebraic relationships that are inherent to what I should say is called Newton's law of universal gravitation. All right, so here's some practice with the relationships in there. And then this is a way for us to, well, ask some questions that we've asked before, but in a bit of a different context, or at least at a different scale. Okay, that's it. Yep, that's it for this. We will tie some stuff together between gravitational field and gravitational force in our next video, which talks about orbits. That also makes connections with circular motion. So we get to really do a lot of good connection of dynamics stuff, circular motion stuff, gravity stuff when we talk about orbits, especially when we assume those orbits to be circular. All right, folks, farewell.